Chapter 3.2 Inertia and Newton's first law. Is force needed to keep a body moving? Aristotle believed that a force is necessary to keep a body in motion. But 2,000 years later, Galileo proposed a thought experiment in early 17th century to disprove Aristotle's idea. In his thought experiment, Galileo argued that the ball, in order to return to the same height, should move forever along BF, until one day the rail rise up again. So a force is not necessary to keep a uniform motion, that is, a motion with uniform velocity. Experiment 3A demonstrates the idea using a data logger and a frictionless air track. The following setup is used to study the effect of friction on motion. There is a glider with a reflector at the end of the air track. The motion sensor will detect the motion of the glider. We start the data logging program and shows the displacement time graph. Then we turn on the air pump, and in this way the air track becomes frictionless. Softly push the glider across the track, and this is the displacement time graph that we may have. Now repeat the experiment by turning off the air pump when the glider is in the middle of the air track. The displacement time graph looks like this. Compare the two displacement time graphs. So what is the effect of friction on motion? And so we see from the experiment, without friction, the glider may move at constant speed, but when there is a friction, it will stop very soon. 2. Inertia and mass. Galileo also proposed the idea of inertia, which is the tendency of an object to maintain its state of motion, as it is more difficult to change the motion of a more massive object. A larger mass is a larger inertia. So mass is just a measure of object's inertia. You can easily find YouTube video about tricks that make use of inertia, and many of them are pretty interesting. Indeed, your teacher will certainly show you some and let you try in the next lesson. Isaac Newton further developed Galileo's work and formulated 3 laws of motion. The laws are pretty simple and concise statements, and yet able to explain almost all motions in the universe. The first law states that every object maintains its state of motion unless acted upon by a net force. In other words, a mass remains at rest or keep moving at constant velocity must experience zero net force. Let's see how we may apply the law in the following situation. A dog sits still on the ground, is at rest. Its weight must be balanced by the upward force, the normal reaction acting on it by the ground. An ice hockey puck moves at constant velocity on the ice should also experience zero force. Its weight is, again, balanced by the normal reaction by the ice surface, and the friction acted on it must be negligible so that the velocity does not decrease. When the car brakes suddenly, the car decelerates as the brake applies a huge friction on the car. The passenger inside does not experience the braking force and so jerk forward due to their inertia. The passenger may hit the dashboard, and passengers may even hit head-to-head in a minibus, which often results in injury. So passengers should buckle up, that is, to wear a seatbelt, to prevent them from jerking forward when the car stops suddenly. Similarly, when the car is pumped at the back, the passenger's head tries to remain stationary due to its inertia. Head rests are used to prevent head and neck injuries in such cases. In example 2, you have to find the forces acting on the car by the ground and the tension in the cable. You should note that the tow truck and the car are both moving at constant velocity. In this case, they both should experience several net forces. And so, for the vertical forces, their weights are balanced by the normal reactions acting on them individually by the ground. And for the horizontal forces, let me leave it to you. Example 3 shows a more familiar situation to those who ride on MTR often. In Figure A, the train is traveling at constant velocity. Due to inertia, the body moves to one side when the train accelerates. In Figure B, the train is accelerating to the right. Well, it may be traveling to the right and accelerating, but it may also be traveling to the left and decelerating. Similarly, in Figure C, the train may be traveling to the right, but decelerating, or it may also be traveling to the left, but accelerating, and the accelerating points to the left.